Hi, this is the first in a series of videos that I'm making to support you with doing the worksheets that I'm posting on Show My Homework. By now you should have looked at the YouTube video that I directed you to, and that gives you a very good insight into how to solve problems when we have components wired in parallel, not series as we've already done in class. But nevertheless, I'm going to give you some worked examples from the sheets that I'm setting so that hopefully once you go through those with a little bit of thought, you should be able to proceed and get over any times where you're a little bit unstuck. So this is the simplest of all the problems. We have two resistors there in parallel, both single resistors in parallel with each other and both identical values. So if we're going to add those two resistances together, it's not series, that would be simple, we would just add the two numbers together. It's parallel, and our video has told us that therefore we need to use an equation which is 1 over RT, the total resistance, and that equals the sum of 1 over each of the individual resistances. So in this case I've got two resistors, so this is 1 over R1 in the single branch and 1 over R2 in the second single branch. Now if I had another resistor here, I could call that R3, then of course my equation would just continue and we will keep on adding terms, but we haven't, so we won't, and we'll keep it nice and simple and get rid of that. So it's simply a case now of substituting in. So 1 over RT equals 1 over, my value is 5 ohms, plus 1 over 5 ohms. We're in there. Tidy that up a little bit. 1 over 5 ohms, and so if we add those together, you should be very familiar with adding fractions. So that gives me a number 2 on the top, number 5, the same number underneath. But that's not all of it, and this is where so many marks get thrown away because there's a final stage. At the moment we've got 1 over RT, but actually we want RT, which is RT over 1. So we have to turn the whole thing upside down. So RT equals 5 over 2, and that equals 2.5 ohms. So that's how to add two resistors, one in each branch, together in parallel. See you in the next video. Hi everybody, this is the second in a series of videos. What we've got now is we're just developing the problem that we had previously. We've still got the two 5 ohm resistors, each one on its own individual branch, but being connected together in parallel. And we want to know something which is this value here, which is what is the current that will be read if we were measuring at that point, and that would be the current for the whole circuit. So there's many ways to solve this, and this is one method. So what we could do here is we could say, well, I've got these two resistors, and if you remember from the last video that these combined, when added together using our equation, gave us a total resistance of 2.5 ohms. And so that would allow us actually to just redraw this circuit. So we could say, well, I've got my circuit here, which is a 10 volt supply. I'm coming down here to my ammeter, which is a 1. And instead of having those two parallel connected resistors, I could just treat that now as one single 2.5 ohm resistor in series. And if I'm able to do that redrawing, the solution becomes very straightforward. because we can use Ohm's law and say that V equals IR. Now then, just changing pen, so I've got V equals IR, so I know V, got that there, and I know R, got that there, and so it's A that I want to find, so that means I must do a rearrange. So I need I equals V over R, and substitute in, so I equals V over R, so that equals 10 divided by 2.5 ohms, and therefore my solution is that I equals 4 amps. So that's one way to solve it. See you in the next video. Hi, welcome to the third video. It wasn't the third video I was planning, but after I finished the last one I thought I'd show you an alternative way to solve the problem of what the reading on A1 is. So I'm going to redraw the circuit first of all, just very slightly, and try to explain to you what I'm doing. So I've got my 10 volts in supply, come down here, and this is the reading I'm interested in, A1 on my ammeter, and my first branch with a resistor in, which is 5 ohms, and my second branch, which also has a 5 ohm resistor. And I could pop an ammeter there and an ammeter there. Now the reason I might want to do that is because we know from the YouTube video that this is the total current flowing in the circuit, but we have a branch, and so at this branch that current is going to split. So the values that we've got over here on A2 and A3 are going to be less than the values on A1. We also know that as the current flows through those, it comes back to another branch here and joins up again. So this current here is once again the total current and is the same as the current that we've got on A1. So if I just write that out, I could say that my reading on ammeter 2 plus my reading on ammeter 3 will equal my reading on ammeter 1. But I can't write it like that really, because I should use the proper symbols. So my current, which would be I2, plus my current, which would be I3, is going to equal the current I1. Just label that up here, so I would have I2 going down here, I3 coming along here, and I'm calling it I1, it could be IT for I total, but there we go. So I've just reset that diagram a little bit because I need to put something else on. So how could I go about finding these values for A2 and A3? Well, I can use Ohm's law. In the YouTube video that you watched, it was very clear that we have 10 volts across these 2 points that I've just marked with the cross, and therefore it follows that I must also have 10 volts between there and there, and 10 volts between here and here, which if I redraw, I could redraw like this, and I could say, right, well, if I put a voltmeter there, that will be 10 volts. If I put another voltmeter there, that would also be 10 volts. And now I can use Ohm's law to solve, because A2 is going to be, I've got V equals IR, and I need to know my current, so it's a rearrange again, so I equals V over R. I've got my value of V, just change pen, got my value of V here, got my value of R here, and therefore I can work out that I would have A2, so A2, so I2 would equal 10 divided by 5, which equals 2 amps, and of course so would I3, because I3 also is 10 volts divided by 5 ohms, so I3 also equals 2 amps, and therefore I1 is going to equal 2 plus 2, which equals 4 amps, and that's exactly the same solution that we got in the previous video. So that's another way to do it. Hope that helps. Hi, here's video 4. This is a little straightforward one to go with one of your worksheets. So no ammeters, no voltmeters. We're just now considering the fact that in some circuits we will have components that are connected in parallel, but they may also have branches where the resistors are connected together in series, and it's a case of identifying what's what. So what have I got here? Well, I've got two resistors here. They're in the same branch, and therefore they're connected in series. Those two resistors are then connected in parallel with that 4 ohm resistor. So in order to calculate the combined resistance of that branch, it's very simple. I supply my laws for calculating the resistance, the total resistance in a series circuit, and therefore that is that RT equals 4 plus 4, so the total resistance in that branch is 8 ohms. Now this 8 ohms combined resistance is in parallel with this 4 ohm resistor. So if I'm going to calculate part B, that was part A because there was only one. If I'm going to calculate part B, then I need to apply my rules for calculating total resistance in series circuits. So I've got an effective resistance in this top branch here, which is 8 ohms. So I've got 1 over 8, and that's in parallel with this single resistor down here, which is at 4 ohms. So this is 1 over 4, and then I solve in the normal way. So if I'm adding my fractions together, then that's 1 over 8 plus 1 over 4, so that's 1 over RT is going to equal 2 over 8 plus 1 over 8. I shouldn't have done that, should I? I should have done it the other way around, otherwise that will confuse you. So I've got my 1 over 8 for my top two resistors together, and I've got my 1 over 4, which now I'm going to have to turn into another 8, so that's going to be 2 over 8. So that means that my total is going to be 3 over 8. But what is it that we mustn't forget? That's right, we mustn't forget that we actually want RT, so we've got to turn the whole thing upside down. So the answer is RT equals 8 over 3, which equals 2.6 recurring. Ohms, but of course we really should round that up. Have only got one significant figure for those, and so in theory it really ought to be 3 ohms if we're working to one significant figure. But if we were taking this on to do further calculations with, we would probably be using a figure which is something like 2.67 ohms. So that's how we would solve that. Hello, welcome to the 5th video in this series on how to do parallel circuit calculations. And you can see that this question that we have here this time still involves the same resistors that we had in the previous question, where we were asked to total up the value of these two resistors at the top in series with each other, and then them being in parallel with this resistor on its own down here. But this time we're going to be required to calculate the values that would be shown on the 3 ammeters. So the first thing to do is identify what we've actually got for these 3 ammeters. First of all, A1, well, that will be reading the whole current for the circuit. I'll say total current, the whole current. But of course, once we get to this point here, then we're going to find that A2 and A3 are going to be smaller than A1, because at this branch we're going to find that the current splits, A1 splits, and therefore A2 plus A3 will equal the readings on A1. And let's write that. So the readings on A2 plus the reading on A3 will equal the reading on A1. But of course, we don't write it like that. We have to use the proper symbols, and so our equation then becomes that I2 plus I3 will equal I1. So I'm just going to pause this video now, tidy up the board, and then we can press on with how to solve this problem. Okay, so I've tidied that up a little bit and redrawn this circuit so that we can have a little bit more clarity for the next explanation. But, oh hello, something's missing. Can you see what's missing? Yep, we've, well, deliberately missed out the 2 ammeters in the branches. And that's because I've noticed while I've been teaching this topic that students sometimes find it difficult to visualize questions when you've got ammeters placed at various points in branches. So I just wanted to make this completely clear and reassure you that these 2 resistors that we've got here in series follow the rules for a series circuit, and that is that it doesn't matter where you measure the current is always going to be the same. And therefore, if I have a meter placed here, if I'd put the A2 here, it would make no difference to the reading, and neither would placing it here, and the reading would be exactly the same here. And also, for the bottom branch, it would not make a difference if the ammeter was placed here or here, where it has been placed, or indeed even here or here. So I hope that clears things up. So let's get rid of those crosses and put in the ammeters. What colour was I using? Okay, so a nice purple. Here we go. So A2 and A3. It's quite the same colour, but never mind. Now the next thing to appreciate is that here I've got 6 volts. And the video that you were asked to watch first of all on YouTube, that was quite clear that that 6 volts is between there and there. And so if we come down these rails, we find that we have corresponding points here and here. So between these two crosses, these two, there will also be a potential difference of 6 volts, and similarly there will also be 6 volts across there. So what does that mean? Well, that means that I can just tidy that up. I can try and pick the right colour this time. Say that here I'm going to also have a voltage of 6 volts, and I also have 6 volts across these two resistors. But this little bit here is rather inelegant. So what I'm going to do now is I'm going to combine both of those resistors into one single resistor with the combined value. So let's do that. Just take that out there, select pen again, and draw in. And what will this value be? That's right, it'll be 8 ohms. And now we've got everything we need to be able to go ahead and solve this problem. So I'm just going to tidy this up and move this big circuit to one side so that we can do some workings out but still see the circuit. So I'm just going to pause the video to do that. Okay, so I'll change pen to red pen. So hopefully that's all still nice and visibly clear. So let's solve for A2, which of course we're going to write as I2, and we can use Ohm's law. So we know that V equals IR, so if we rearrange, we've got I equals V over R. So I2 is going to equal that value there, which is 6. Divided by our resistance for I2 branch, which is going to be 8, and therefore that's going to be 0.75 amps. So then let's just write that up here. So we'll write I2 equals 0.75 amps. And I3, I'm going to solve the same way. I can find the pen. Right, I3 is going to equal, well, we're down here in the bottom branch now, so we've got 6 volts and 4 ohms, so that's 6 divided by 4, which equals 1.5 amps. So let's just write that there. I3 equals 1.5 amps. So I'll just pause again, clear some space. And then our final equation is going to be that we know that I2 plus I3 equals I1, and that'll be the reading on ammeter 1. So 0.75 plus 1.5 equals 2.25 amps. So I1 equals 2.25 amps. And that's how you solve that problem. See you in another video. Bye.